All right, so in this lecture, we will continue our discussion of TensorFlow. And in particular, we are going to learn how to implement an algorithm with TensorFlow. So usually when people, as I've said before, when people use TensorFlow, they think of building, deep neural networks, right? So networks that look like this, right? So you have multiple layers between the input layer, which is this one, this is the input, and the output layer. However, as it turns out, you can build any kind of network with TensorFlow. So if we can build even networks that don't have these hidden layers, and instead that just look like this, right? So, have an input and an output. Right? We can also build these kinds of networks, and these networks are not neural networks or deep neural networks. Instead, they are algorithms that we are more familiar with, like linear regression, and logistic regression. Right? So in this discussion today, we are going to focus on the easiest algorithm that we can implement, which is linear regression. So linear regression is a very good algorithm to start with TensorFlow, because linear regression is very intuitive. Right? So linear regression is very intuitive, and it shares all the basic building blocks with the other algorithms. So the goal is that by understanding linear regression, we can then better understand logistic regression, and then from there we can better understand neural networks and deep neural networks. All right, so today we will go over the lecture on this topic, and then later on also we will do a lab assignment where we can implement the actual code, linear regression code, in our computer using Python and TensorFlow. Okay. So the learning outcomes of this, upon completion of this unit, students will have a better understanding of linear regression and how it can be implemented in TensorFlow. So we will discuss some of the basic aspects, so basic, theory, if you will, of a linear regression algorithm. Right? And then we will look, of course, at TensorFlow, which is, in itself, TensorFlow, we want to understand the mechanics of it, and the mechanics will allow us to, by implementing linear regression, we'll be able to implement other algorithms later on. So what is linear regression? So, if you've taken a statistics class before, you know what linear regression is. We are all familiar with this algorithm. It's the kind of algorithm that, given some information, we can predict a value. So for instance, the stock market, right? So, you want to understand the price of a stock. Is it going to be high, go up or down? Is it going to be 500, or 1,000? Well, so what we do is we correlate input variables, the independent variables, with the dependent variable. All right, so linear regression. Now I should say also that, whenever you think of machine learning, right, you think of basically classifiers. All right, so you think of classifiers. Right, and classifiers are usually things that you give in an input vector of values. You're going to predict one of two classes, right, or three classes. For instance, you predict 0, 1, and 2. However, we don't usually associate linear regression with machine learning. Instead we think of it more as part of statistics. But really, linear regression is part of machine learning because it is technically the same thing. You still give it, so whereas here you give it an input vector into a model, and the input vector into that model predicts the classes. With linear regression, we pretty much have the same thing. We have an input x, right? And then this input x goes into a different kind of model, a linear regression model. Now here's where it's different. Now the linear regression algorithm, instead of predicting one of three classes, will predict, a real valued number. So any number in a sequence, like it might be the price of a house. So the house might cost somewhere between $200,000 and $300,000. But the value that it can predict can be any one of these, right? So it could be that one, $210,000, $220,000, $250,000, $280,000, etc. So that is really the difference between classifiers and linear regression. But if you notice, this is the same. Converting the feature space, right, is the same. Building the model, right? So there's classifier models versus linear regression models, but it's still kind of the same approach. And then the only difference is the predicted value. The predicted value can be classes, or the predicted value can be real value numbers. So linear regression refers to a model for predicting any kind of magnitude, right? Such as housing prices, sales prices, ages, or anything that can be quantified. So instead of just classes, like, for instance, happy, sad, or, intrusion, not intrusion, malware, goodware, etc. In linear regression, multiple variables and coefficients are combined to form an equation that can be used to fit a particular data set, right? So this is the idea that, you want to predict the value y, so you're going to take some x given some weight, right, plus a bias, so, an offset. All right, so you have this information, your input here, right, and this over here is the model, right? And once you create this equation, you have a way of predicting a given y. So this is important because all machine learning is like that, right? All machine learning is about giving an input value, learning the model, and then predicting a value. And really the only difference is here, this y would be this one here, or would be this one here, right? So that's the only difference, if you notice. Everything else from this side on is the same, and only this part really is what is changing. So all you have to do with TensorFlow, is that you have to build these. You have to know how to build these architectures, and the architectures are pretty much the same. Now, once you've designed the architecture that you want to build, which is basically the type of model, so in this case a linear regression model, the next step is you have to decide what's going to be the criteria to optimize that model. So that is called the fitting process, right? The fitting process. And this fitting process involves, an optimization approach, right? So this is where this is interesting, because all models, linear regression, logistic regression, neural networks, deep neural networks, all of them have an optimization approach, right? So they need to have an optimization approach, and the optimization approach is specific to the different kind of algorithms. So in this case, when you took your statistics class, you learned that the optimization approach for the fitting process was something called least squares error, right? So, or LSE, right? So least squares error, and I'll talk a little bit about that, but it's something that is actually very intuitive, and that's the optimization, right? So usually people will say minimizing the sum of the squared errors, etc. So the coefficients or weights for each variable are useful in determining the contribution of each variable to the fitted model of the data. So these coefficients refer to this W, which in machine learning, maybe when you took the statistics class, you called these the coefficients. In machine learning, the terminology is usually the weights, right? And the key intuition with when you hear the word weights is that it implies, the contribution of an input. So for instance, if you're trying to predict, housing prices, you might say X1 and X2, where X1 represents the square footage, right? And then x2 might be, is it, water, is it near a lake or not, right? So lake property, yes or no, right? So these two elements indicate, obviously, the price of the house plus some offset over here. But it might be that, you need to determine which one of these variables is more important. Is it the square footage or is it the lake? So it might turn out that this one is really important, 0.0 or 0.5, let's say. And then this one is less important, and it might be 0.002, for instance, right? So that's kind of what it means, that you're trying to learn the contribution of the variables. And so, as I said before, that's what the model is going to learn given the data. So the coefficients or weights for each variable are useful in determining the contribution of each variable to the fitted model of the data. So now that we sort of have this intuition of what linear regression is, let's focus now once again on least squares error. So this is least squares error. All right, so this is something that we are all familiar with when we looked at in statistics, right? So as you can see, the equation here is made up of two elements, this element y, and then this other element here, which we can call y hat, right? So really you can think of it, to simplify it, just like that, right? So what we're trying to do is called least squared errors because we're trying to minimize the difference between these values. The square value is just added here to get rid of any negative effects, because you're going to end up, because of this symbol, you're going to end up adding things. So you don't want to have -3 plus -2 plus 2, because they'll like cancel each other out, and that's not what you're looking for, right? What you're looking for is actually to get rid of that and to add all of these differences so that it ends up being like 7. All right, and so because of that, we have the square value there. But the objective of this is actually to compare whatever data we have in the test set, like this. So this is the test set, given the samples. We have the actual annotated data or the real data, and this is the y. So we already have these values, and what we're trying to do here is we're trying to build a model, y hat, which is basically wx plus b, that predicts that value. So that's the optimization process, and the objective is to find the optimal w and b, right, that when plugged into this equation plus the given x in the test set, it'll predict a y hat that is as close as the real y. All right, as close as the real y. So for instance, let's say that the values here for y are 10, 11, and 8, right? Now we pick at random some values for w and b, and then we plug in the same x, and now we get a y hat that is like 3, 17, or 170, 0, right? We take the difference between these three values, and they're going to be pretty large. So they're going to be, let's call it like 7, and then this one's really high. It's like 159. And then the other one is 8, right? So those are the differences. So if we add this up, it's going to be a really high value. So we're going to say, well, we picked a W and a bias for this model. Let's call them W1 and B1, right? And that defines a model that gives us these differences. Then we pick another set. Let's call it W2 and B2. And it turns out that when we do W2 and B2, let's say this is Y1, and then now we're going to predict Y2 just to see. Now this one, these set of parameters give us values like 8, and then 7, and 6. So now if we take the differences between these values, we're going to see that the difference between 10 and 8 is 2, and the difference between 11 and 7, that's like 4. And the difference between 8 and 6 is 2. So if we add these numbers together, we can see that this is 8. So the difference here is 8, whereas the difference here was somewhere above 150, so greater than 150. So what does that tell us? It tells us that this model here is better than this model. So the previous model is not as good because the differences between the real values and the predicted values were really high. Whereas here, the differences were small. So that's the better model. And so that's the optimization objective that we are looking for when we apply least squares error. So it's one of the most intuitive equations that we have out there, and this is how we learn the parameters in the model to be able to build a model that is as close as the real data as possible. So in this equation, you can see here n just represents the number of samples, right? So we're going to do this. We're going to build this model for all the samples that we have. Another way of looking at this graphically is like this, right? So here we have this equation, the equation wx plus b equal y is actually this line, right? That line represents the equation. And then the points that you see scattered here represent this one, right? Represents the y. So it represents that. So the y is the points, the actual data, and then this one, which is y hat actually, represents the line. So y hat, let me just draw that here. So y hat is the line itself. So it's the same idea, right? So we predicted this line kind of to fit the data in some way, and now we just want to know, we want to pick a line that minimizes that difference. So for instance, let's say for a given value x, right? Given value x, this one, right? So if we go over here, we can see the real value is this one. And then if we go all the way to the line, we can see that the model predicts this one. So basically the difference between the real and the predicted is just that, right? And that's the little difference that we want to add. The same happens here. So for instance, we picked an x, right? And then this x is the real value, but then if we continue for that x all the way to the model, that's what the model predicts. So obviously here we have a much bigger distance, right? So the delta or distance that we have available there. And so that's the same concept as over here, that we sum all of these values. And so we want to fit a line that's the best. So for instance, if I created this line, all right, I use that line, I perform the same operation. I pick this value, x, and I go all the way over here, and now I see that is the real value. And so now, oops, this is going to be the distance for this line, right? So for this, I'm going to paint this in blue. So this line, this blue line actually predicts that the value for this x would be here, whereas the real value is there. If we pick another one, let's say this x here, some other x, if we go to the real value, that's the real value. The predicted value is here, so the distance between these 2 points is that. So as can be seen, these deltas in blue have higher distances than these deltas in red. All right, and so given that, the optimization objective here is to select the optimal line that minimizes these distances. And so obviously between these two lines, this one has the, minimizes those distances. So it's the optimal one. So in linear regression, a line is fitted to the data set in feature space. Feature space is basically, any Cartesian plane that we define here for our features, by minimizing the sum of errors. That is to say, the sum of the error distances between the values of the predicted line, which is, the blue line here, and the real values, which are the actual points. So this simple equation defines the linear regression model, right? So that, you've seen it probably when we see this in school, m, right? The slope as well. Or, we think, let's use y hat, w, x plus b. So that's the model that we are using. So this simple equation defines the linear regression and the parameters that must be learned given the training data. So these are the parameters that we are actually learning in this model, right? So they're the model. That's what they are, given the training data. With this theoretical framework, I will now proceed to describe how to code this with TensorFlow. So hopefully now we have an intuition of how, we have basically, some data. We've defined some equation that we're going to build. The equation, as you can see, defines a simple line in a vector space. And so given that knowledge and the fact that we know that we're going to use least squares error, we can proceed to build a model in TensorFlow. So the linear regression model will be shown in the code below. The purpose of the code below is to be simple, right? And to show how a linear regression algorithm can be implemented in Python using TensorFlow. So there are various other ways that we could implement this code, more modular approaches, etc. But for our purposes, we're just, I'm just going to keep this simple. This will be our very first, TensorFlow algorithm that actually, does something. But what's important about it is that this should capture a lot of the elements of what we need to have to define an algorithm in TensorFlow. So for our example, it's always good to have an example when we do things. So we are going to assume a very simple linear regression problem for housing prices. There's also a lab associated with this, and I'll describe the lab after these slides. But the lab will be basically to implement this algorithm in TensorFlow. So we are going to assume a very simple regression problem for housing prices. So let's just call this example for linear regression. So it's a simple example for linear regression. So what do we need to have here? So we are going to have one input, or that is to say one feature. So usually, to put this into context, when you did Iris, the Iris data set, which is one of our easiest, we had what? We had the class, right, which was Setosa, Virginica, etc. And then we had four features: F1, F2, F3, F4. That's what we had for that data set. Right, so it looks something like that. And that was our classification problem. In this example, we're going to do housing prices, and to keep it simple, I'm only going to use one feature. So this example, housing prices, will just look like this. It will only have one feature, F1, and it will only have one value here, but it's not going to be a class. Instead, it's going to be a magnitude. So really, it's a very simple data set, right? We are going to have one input feature X1, in our samples, which is going to be the size of the house. All right, so we're going to say that a house is so many square feet. So 1,000 square feet, 2,000, 4,000 square feet, etc. All right, those are the inputs, and then the predicted value, the y here, will be. We will have basically one output value, which is the cost of the house. So as you can see, this will not be like with Iris, where it's one of three categories. Instead, this can be any value. This will be 200,000, and then this one could be 250,000, and then this one could be 400,000, right? But any value in between, it could be more. So it's a wide range of values. Right, so that is the difference between a data set like Iris that we saw before and a new data set, the data set that we're using in this example. Therefore, we will have an equation that looks like this, right? So our equation at the end of the day is y, the value that we're predicting, given some weight that we have to learn in the model times the x value, x1, which is the square footage, plus bias, which is part of the model that we have to have in linear regression. All right, and so we end up with something like that. Now we will need to solve this equation by learning the values of wi and the bias. So these are called usually the parameters in the model. And what we are given in the training data is x, the x values, which are these, right, and the y values, which are these. So this here. Okay. Now let's imagine that, just to clarify it a little bit more, for an equation with two input features, such as, this one, right? So for an equation like that, y equal w1 times x1 plus w2 times x2 plus bias. All right, so this equation would mean that we have another feature over here, right? So let's say f2, and f2 represents, for instance, that the house is, lakefront or something. So lake, no lake, lake. Right, so it's something like that. So we add a second parameter to our features, and so we end up with, now we have to represent that by adding a second feature to the equation. And as you might imagine, this is how equations can scale from just having the one feature to having multiple features. So for an equation with two input features, such as y equal w1 times x1 plus w2 times x2 plus b, we can show it in a diagram form, as can be seen in the next slide. And you can see that here. You have the linear regression model. We are predicting the y here, right? And we have two inputs, x1 and x2, and then we have two w1, a w1 and a w2 that have to be learned. Now, if you notice, this slide is very interesting because this reminds us of a neural network, right? What are these? These are neurons, and this is a network of neurons that are connected. It's very simple, but here we have our very first network. And so this intuition allows us to see, well, if we're building neural networks in TensorFlow, right? We know we can build neural networks in TensorFlows. And even though this is linear regression, this also looks like a network. So that means that we can model a linear regression model, and basically almost any model, as a network, right? Or many models as networks. And so we can model them in TensorFlow. Okay? So now remember that for our previous example, we are actually only going to use one feature and one class. So in that case, if we want to build that model is even simpler, right? The model only, instead of looking like this one, it's basically just that, right? So we have one x1 input, we're going to learn one weight, and we're going to have one predicted value. So it's even simpler, but even such a simple example is still a network, which means it can be modeled in TensorFlow. And if anything, that is the great intuition of why we can build all of these models in the TensorFlow framework as networks. So as shown in the previous equation, a linear regression is an equation made up of three main elements: the x, which is the data, the w, which is the weights that we learn, and the bias. So these are the parameters in the model, and this is our training data. Our training data. X value here holds the training data, the features. So that's going to hold this. Right, so the information here, the x-is this here, that's the data that's going to be in that variable. So the X value holds the training data features. W represents the weights per feature. And B is the offset value, which is called the bias, which are all parameters defined for the equation, which are learned by the model. These values are directly coded into our algorithm using TensorFlow. So now that we understand this concept, now we're going to start basically trying to convert this into actual TensorFlow code. Right? So in the code below, we will see that that after the library declarations, we will need to define 4 variables. All right? And those variables will be these. All right? So we will have an X variable for the data, a Y underscore variable, right? And then the W and the bias. Notice that this W is actually an uppercase W because in TensorFlow, as a common style, whenever you do something uppercase, it means that it's a matrix, right? And we will learn that everything that you build in TensorFlow is one of the challenges of it sometimes is that things have to be either vectors or matrices. All right, so we don't actually think in terms of just individual scalar numbers. We are actually thinking in terms of vectors and matrices. But anyway, intuitively though, we know this is the weights, the bias, which is the model, and this is basically our data. So data, model. So let's take a quick peek at the code itself, and then we can come back to this slide. These slides. All right, so here's the code actually that we will need to implement for this model. This is about half of it. The other half is over here. Well, there's actually this part and then this part, right? So it's actually, I have it broken up into 3 slides. When I do this in the lab, and we'll type it up, and it'll become a little bit, we'll have the chance to implement this and get it to work. But for now in the slides, I'm just going to describe this. All right, so as we can see here, this is the linear regression code implemented in TensorFlow. I've broken this up into 3 segments, so that's, it's kind of sequential. So this is the first part here, and then we have this part here, and then we have the last part, the main loop. All right, so in a previous lecture or video, I discussed how every TensorFlow algorithm is basically made up of certain sections. All right. Now, when we do the lab session, we will have an opportunity to type this up and actually try to solve this code and see how it runs. Right. So for now, I'm not going to run it. I'm just going to explain how it works. But then later on, we'll get an opportunity in the lab to run it. So what are the main sections here of this code? So we have the libraries. So let's just say libs over here. Then we have a section for defining, variables. As you can see that there. Then we have a section for defining the architecture and the elements of the algorithm or the model. So in this case, we have all of this section like this. All of it, actually. Now what this is doing is this defines the model specifics and also the computational graph, right? So this is, our computational graph in TensorFlow. Now remember that nothing gets run until you create the session. So that's what we have over here. So the next step is to define the session variable, and we run something. So in this case, whenever you create a graph, you want to initialize the elements in that graph, the data types, etc. So we use something like this. Right? And then finally, once everything is done, we have the main loop. So this is the main loop of the code where we actually do the training. So I've broken this up into 2 parts. I have like a for loop for the train section, and then I have a for loop for the test section. Right? And so I'll explain this in a little bit more detail as I go through this line by line. But those are all the main elements of this implementation of linear regression in TensorFlow. So let's go back to the beginning. All right, so the first part of this is to obviously bring in the library. So here we're only using the NumPy library, and then we also have the TensorFlow library. So import TensorFlow as TF. The next section where we define the variables, as you can see, we are defining several 4 variables. We are defining an x, a y underscore, a w, and a b value. So these are, if we think of the original equation, y hat equal w x plus b, and then if we also think of the optimization equation, which was y minus y hat, if we think in terms of that, this y hat is actually that y. Or this y underscore is actually that y. This x represents the data. This w is the weights. This b is the bias. And then you might ask, so what is y hat here? Well, y hat is down here, right? Is the actual model that we built. So because TensorFlow is really about creating a computational graph, it means that we have to, break it up into all the nodes. And the nodes are usually like these variables, these buffers in memory. So we define them, and then once we have all these nodes all over the place, we have node, node, node in the graph, then we have to do this part here where we actually start to connect them together so that we start building our computational graph. So, all right, so now that we've done this part, all right, so let's focus a little bit more on the specifics of the variable. So if you notice, we have here 2 ways of representing or creating a variable. We have TF variable, and we have also TF placeholder. So TensorFlow has this separation in the definition of variables because one is usually more specific to lots of data, which is this one. A placeholder is really a thing that is meant to be reused over and over, right? So you have a placeholder, and when you think of your data, right, you're going to give it batches of data that could be thousands of records, and you're going to give it a batch, and then another batch, and then another batch, and so on. So in that case, TensorFlow has defined a type of variable called a placeholder that is very efficient for that purpose. Whereas if you define something like a tf.variable, these are usually model variables. So they're not necessarily data variables that are coming from the outside, but instead they are the variables that we are learning in the model. All right, so in the we have a network like that, so they're the W's, right? So these are internal, W1, W2, these are internal to our model. Okay, so here then we do, to declare the x value and the value, so the values that hold the, let's say, the train data and the train labels, we're going to create x and we're going to create y underscore. So to define the variable x, we do tf.placeholder, we define the data type, which is tf.float32, and then we have to define the dimensions of that. So notice that this is a 2-dimensional array, if you will, so it's a matrix. So as I said, pretty much everything that we do in TensorFlow from now on, because of efficiency, is going to be defined in terms of this, in terms of dimensions of a matrix or a vector, etc. All right. So let me erase these here so I can use up this space. All right, so let's take this x then. So x is like this, right? And we are saying that our data is, because of these dimensions, it's actually something like this. So none and 1. So what does that represent? None represents, it doesn't mean that there is no value. In fact, it means that the value is really similar to n. It could be any size. So we just write none there because, as we start adding our data in, we might want to pick different batch sizes, for instance. And so sometimes we do batch sizes of 1,000. Other times we do batch sizes of 2,000. And so by doing this, we allow that flexibility in the algorithm without having it to hard code it. So really, we can give it batches of any size. Okay? And that's what that defines. And then 1 just means that we have F1, just one feature. So if you remember in the slides, our data set that we're using only has this one feature here, and it has the 1 magnitude. And so that is what we are capturing in this data. So at this point, we've defined x, right, the x value, and as we can see we define a matrix. Remember that TensorFlow gets its name from the fact that everything is a tensor, right? And if we remember, a tensor is it's a matrix of any size. Could be one-dimensional, two-dimensional, or hyper cubes, etc. Right? So it really doesn't matter the sizes of it, but these are basically the tensors that we are defining. So that's kind of the approach that we take. So let's look at another example. Define now the y underscore, right? So y underscore, that's another placeholder, right? Because it's going to load data. So we're going to do tf dot placeholder. It's going to be float type, right? And then the dimensions again. Given that it's a placeholder, it can be none, which basically means it is n, size n, for the number of rows that we're going to load. And then we say that it is 1 for the dimension here, and that just indicates that we only have 1 column in this, which makes sense because this is the magnitude that we have in the data. If we go back to the previous slide, we can see this references this part here, right? So that's what we're referencing, these values in this column, y magnitude. So now, in the code, we have defined also the dimensions of the y underscore. And the 2 placeholders for our data are now ready. Now the next part is to define the model variables, right? So these model variables. So w will be a tf dot variable here. And if you notice, w is defined in TensorFlow as a tf.zeros, which basically means that we initialize it to a whole bunch of zeros, right? So it's something like this. Imagine some matrix made up of a lot of zeros. Okay? But here, again, we have to define a tensor of specific dimensions. So really, now we have to take into account the dimensions, and so this is going to be dimension 1 by dimension 1, right? So there's only 1 row and 1 column, so really there's only 1 0 there. Now if you remember, this is exactly what we had over here, right? We had this little model over here, right? And we said, given an x1 and a predicted y, we are just going to learn 1 weight for the 2 neurons, right? So this is no network. So actually, what's important here, though, to keep in mind, that this model here is captured, or that architecture. So this is the very first place in TensorFlow where we start to capture architecture. Because this says, when we look at this 1 and 1, let me erase this part here. So when we take this 1 and 1, it's almost like we're saying, we said it's 1 and 1 in terms of a matrix, but also in terms of the neurons that this represents, in terms of the model that this represents, we know that this is 1 neuron, this is 1 neuron, and this is the weight. So really, whenever we define a weight matrix in TensorFlow, we are actually capturing a little bit of the architecture of the network itself by saying one neuron on this side, which is the input, if you will, or the previous layer, and the next layer. So let's just generalize this to layer 1 and layer 2, for instance. All right? And so we are really, or actually to be even better, let's say Li and then Li plus 1. So that's really what's happening here, is we capture in W the relationship between, the neurons in the previous layer and the neurons in the next layer. Now this is going to be very consistent throughout all of the TensorFlow algorithms that we will do, so you will see this over and over, and this is a very important concept to try to remember. All right, the last variable in the model is the bias, and you can see again we do TF variable, and then we initialize another matrix. Let's say here B, right? It's going to be, again, a little matrix made up of zeros, right? Like that. But the zeros are actually just 1, right? So we just have the 1 value, and so there's only going to be 1 bias. So remember that the bias is usually ties in to the predicted value, all right? So so when you have, for instance, this diagram here, you might have 2 neurons here, but the 2 neurons go into this Y, and the bias is usually whatever this Y is plus imagine B, right? So it's really tied to this part of the network and not to that part of the network. So here, usually then, another intuition that you can think of is that whenever you do the W and it's 1 and 1, then this number is usually going to correspond to that number, right? So if you had a 2 here, then you probably have a 2 here, right? And that's kind of very consistent in the code, right? But anyway, so we've now defined the bias to be like that, right? A simple, matrix or scalar of 1 value. All right, so now at this point we are ready to move on to the next section of the code. So we have defined the variables, right? So we've defined the variables, and now we're going to move to the part where we define more of the architecture and more of the model and the steps of how to train the model. So the next step is to focus on this part of the code, right? So this is our model itself. So we said initially that the Y, this Y is actually the Y hat in the model, right? So that's what we're predicting. So it's the predicting equation. So if you look, this was the equation. This is W times X plus B. Well, actually, that is captured right there, right? We used the built-in function matmul from TensorFlow. This is one of the most powerful functions. We'll be using this a lot. It does a lot of the heavy lifting of TensorFlow, performing matrix multiplications, right? Now, just as a side note, if you think of GPUs were designed specifically to do matrix multiplications. And so this is the function that was defined to optimally use GPUs and their power to multiply different kinds of matrices. Okay. Here then we take X, which is this value, the data. There we go. So we take X, and then we take the W, this one, which is this one here, right? And so we multiply those two, which is what you would expect to do in the equation, and we add the bias, which is that one, right? And so just like we would write the equation, just like we would write this equation in, on the board and on paper, etc., we also have the ability to write the equation in TensorFlow exactly as it is. All right? So once we've defined that equation, we've basically defined the model. It turns out that a lot of the algorithms that we do in TensorFlow will look exactly like this. They'll have this equation format, maybe with a few modifications, but it will always be the same principle, because in machine learning, you always have some input data and you have some weights associated with it. And that's usually best done with a matrix multiplication. Once we've defined the model, which is this, the equation, the modeling equation, we need to define, if you remember, the optimization approach. And in particular, we need to define the algorithm to train, so the algorithm to learn, let's say, and also the cost function. So the cost function is this one, and the algorithm to learn is this one. All right, so those two lines basically capture the elements of the optimization. So here we have the cost function, and if you notice, this cost function captures that y minus y hat square and the sum of it. So this equation, the LSC that we saw in a previous slide, is actually represented really nicely, I would think, in this code here. You can see we give it a name like cost or something like that. Then we have the reduced part, roughly can be thought of as this part here. And then we have this tf.power, which basically represents the square part. And then within, we have this, right? And you can see that's a y underscore minus y, which is the same as saying the real data minus y hat, so that is our model. So the cost function is captured here in this equation. So now we can say that this is the cost function, basically that. Okay? So a little bit of TensorFlow, as you've seen by now, pretty much every time you want to use something from the TensorFlow library, you say tf.reduce sum, right? So this is the, as I said, reducing, adding up the values in the vector. I'll provide a more formal definition of this function in the next few slides. tf.power is just basically a function tf.pow that takes some value x and then the parameter. So this function is like visualizing this mathematically speaking, right? So raising something to the power of something. All right? And then as I said, these two elements are just this part, the actual values and the predicted values. So the next step in our code is to focus on this. And as I said, this is part of the optimization. This is the learning algorithm. And if you look at it, we are looking at something called gradient descent. For most of our machine learning examples in this course, or most of our deep learning examples, we will use the gradient descent algorithm. Gradient descent, there's a lot of theory that goes into that. Luckily, though, we don't have to worry about that because that is fully implemented in TensorFlow. So it's basically abstracted. We don't have to worry about it. We just have to know that we are going to use that algorithm. All right? Not in this slide, but in another set of slides, I will go into a little bit more detail about gradient descent and optimization itself. But for now, let's just assume this is the algorithm that we use to learn. So what are the things that you need? So again, we have we give it we create an equation or a function call, and that returns to the value train step. Gradient descent is in the tf.train library, and then we have to specify several parameters. So we have to specify the step size. Right? So if you remember in a previous slide, this is one of the parameters that we define, step size. And then we also have to tell it what we want it to do. So in this case, we tell it that we want it to minimize, and we tell it what we want to minimize, which in this case is cost. Now, one other important point I want to make here is that because in this code we are building a graph, if you look at it, what we are doing is we are defining in all of these different nodes, right? So we're defining different nodes of the graph. So for instance, initially we define a node called x and a node called y underscore, then we define another node called w, and then we define another node bias, but they were kind of all over the place, right? Then we defined this node, right? So we define that node, that's another one, y, okay, so we have that node, and they're still all over the place, except that at this point, y starts to connect the dots. But the moment that I created y, I start to link things. So I tell it, okay, the first thing I want y to do is I want it to do a mat mul, right? Because that's this part here. So I just created a mat mul node. Okay, so that's linked, right? Then I say that mat mul should multiply the elements x and the element w. So you can see that the graph is now starting to take shape, right? And then the result of this, the mat mul of this should give, let's say a result, which is then added with the bias. And so you can see now that the graph, whereas before we had a whole bunch of elements that were kind of separate, now all of these elements are put together in a graph. And the only element we have that's not part of the graph is that y, right? But if you notice, that y is now included here, right, in the next line. So the next line will link other elements. So now we're going to create a new, right? So if we look at this line of code here, now we have a new node called cost. And cost is, it's associated with a reduce function, and it takes now another function, another node called pow, and then pow is going to link y underscore here, so that's y underscore, with that y. And you can see now then the graph is starting to take shape. We are writing this code, but the code is actually linking up everything really nicely. So, we took pow, right, and then pow actually, to be very precise, pow was linked with a minus, and then the minus is really what is linked to these elements. So there's your graph. That is your computational graph, and we define all of this via the code, right? Pow actually is associated with a 2 here, right, and so on. So this is the way that we build a code, and then the code can represent a computational graph. So we were looking at the graph that we just created here, right? Based on the code of, how to do the model with the y, and then the cost function, right? And then the training algorithm with gradient descent. Right, so as we can see, we've linked up all of the elements that we created into this graph over here on the lower right-hand corner. Now, usually the last part in this section, sometimes you could, let's say we can, think of this as 4 items that always go in this section. So we have the inference or the prediction function, the cost function, the training step or training approach, and then finally we have a 4th section here which we can call the evaluation. So this is the evaluation section. So the evaluation is the part where we measure the performance of the algorithm, right? So that means that we're going to take, let's say, the predicted values versus the actual values, and we're going to calculate how many of those are correct. So for instance, if we have the real ones are 1, 1, 2. The predicted ones are 2, 1, 2. So this is a match. This is a match. This is not a match. So that's 0.66% accuracy. So that's usually what we do in this evaluation part. Since this is not a classification problem, we're not going to write that function at this point. Instead, all we're going to do is basically something like this. Okay, so in this section, the y, which is the inference, is the predicted value, and we just want to output it out. But to kind of separate the logic between what inference is and the evaluation, we can just simply assign y to another variable, eval op, and then that eval op can be the variable that you use sort of in the evaluation section. What you see here is the same thing as this, except that because of the way the variable is calculated, we want to typecast it into float specifically, so we use the Tensorflow cast function. And then this part over here just basically removes the bracket. So, when we get this, let's say this is 26. So when we get this answer from float val, it's going to look like that. After applying this function, this will turn into just a regular 26. Right? Because we get the sum. We basically do like the mean of the values in this array. Since there's only one value, we really just get 26. All right, so that kind of concludes this part. This is actually, kind of the most difficult part of the entire TensorFlow section for linear regression. In this section here, we are going to focus on the session. So this should be pretty straightforward. This is the session section, and all we do here is now, once we've created this graph, the graph over here, that graph, now the graph basically is defined, but it does not exist in memory. So this is similar to like when you do object-oriented programming. You define a class, but the class doesn't really exist. There's no instance of it until you do something like new class. All right, so this is what we do in this section. We'll take, we create a variable called session, which is a tf.session variable, and then this session, we can actually now run the graph, so we do session.run, and then here what we're going to run is the variable init. Init is basically a simple function that exists in TensorFlow that allows us to, now that the graph is defined, we can go ahead and generate and populate all the data types and everything like that. So this follows directly after the previous code, and it just now makes kind of makes the graph be an instance, let's say. Right, so think of it as the space is now allocated in memory. All right, so that's kind of what's happening here. All right, and then the next section is the main loop. So this is the main loop. So this is, remember that we said at the very beginning when we started our discussion of deep learning and TensorFlow that these programs are iterative. Right, so they're iterative. All right, and so here this is the main loop. And for convenience, although I could have just used one loop where I do both training and testing, I have actually divided this out into train and test just to make it a little bit more obvious. So if you see, there's one for loop here and one for loop here. So remember, this is a very simple example, just two variables, housing prices. So we're saying that this is square feet, right? And then we're saying that this is the price of the house. Okay, so now that we know these values, or now that we have these, this is the data that we're going to use it. We're not going to read in data. In previous examples, we've used things like gen to txt or something like that to read the data in from a CSV file. In this case, to simplify things, we're not even going to read data. Instead, we're just going to create the data randomly. So if you look, all that's happening here is we have a for loop from I to 100. So we're going to do 100 iterations of it. We will generate our data basically not randomly, but automatically. So we can say that this is ys and this is xs. So we're going to we're going to use NumPy. NumPy is one of the libraries in Python that will allow us to create a simple little vector here, an array of NumPy, a NumPy array. And so this array will consist of the index values. So we're saying that we go from 0 to 100, so 0, 1, 2, 3, 4. These are just examples. Those are that's the square footage of the house, every iteration. And then the ys is just simply this number, because you can see I times 5, so it's just going to be 5 times this. So it's 5, 10, 15, and so on, right? So basically the correlation here in this model is that the price of a house is basically 5 times its square footage. Right? And this is just a made-up example that we've done to kind of illustrate the last part of TensorFlow here. So once we've generated our data, we have this ... So that's going to be our, now instead of reading it from a CSV, we just generated it, and it exists as an XS and YS vectors. Now the next part is something that is very particular and specific to TensorFlow. TensorFlow has something called the feed dictionary. You can see it here. Feed dictionary. It's a built-in variable where you provide the data. Remember that we don't run the code until we run the session. So what needs to happen is you define your data somewhere in the Python code, and then you pass it into the graph through the session. So for instance here, I've created this variable called feed. It's a dictionary, right, of that contains the value xs and ys, which are these, right, the data that we just created. And we're saying that that data should be mapped to the internal placeholders x and y underscore. So if you remember, x and y underscore are here, right? So we go to this section, you can see that here. So you can see that here, these are the placeholders, right? So we created x and y underscore. Those two variables are the ones in the, if you remember in the graph over here, they are this one, right? And this one, right? So those two nodes in the graph now need to be populated with data. They're no longer just defined. Now you need to link them to some actual data. And so that's what you're going to do in this part over here. You go ahead and you take the XS and YS data that you generated and you assign it to the placeholders y underscore and x. And that's done through the feed dictionary. So once you've created this dictionary, then we are ready to call the session run. So here it is, session run. And session run takes two parameters. It takes the feed dictionary, which is this one, which is, I just explained what that is. And then you tell it, given that feed dictionary where you pass the data to the placeholders, also run now train step. So what is train step? Well, train step, we have to go back to the code, and we find that train step is actually this variable. All right, so in the graph, it should be train step, another node, and look at this one. So train step is linked to cost. So it's linked like that. All right, so now when we run train step, we actually have access to all of this in the graph. All right, so we are, and notice that by calling train step, we basically call the gradient descent optimizer, which uses the learning rate 0.0001. Then we minimize the cost function, which is this. The cost function, as we know, is a reduce here, right? That is linked to y, the y here, and also this y here, and so on. So you can see how everything is linked together, and just by calling one node, train step, we actually end up calling everything else in the node that is linked. So basically that tells us that all these functions, the y, the cost, train, plus all the variables, etc., are all linked in the graph, and we get to run and execute the graph via train step. So that's how that works. All right, once we've generated train step, the model basically takes in data, and now what's going to happen is, the optimization takes place, and going back to the graph, we can see that, so the only nodes in the graph that were not defined were the W here and the bias, right? So those are the values that now, or the variables, right? These ones over here. So these variables will now become executed, basically. So through the gradient descent optimizer, through the minimization process, given the constraints, the model and the data, the model will learn the values, the optimal values for W and the bias, right? And then, so now that completes the entire process, and now our model, this one over here, our model here, is now ready to be used. So we've now calculated our inference function. So at this point, basically, we've trained the model, we repeat this for 100 iterations, and then we can just do a print, simple print, to look at the final value. Now, once we've trained the model, this for loop finishes, and now we set that this is going to be test. So now we're going to test the data. So for that, we kind of repeat the process. We're going to do another for loop. Now this time, notice it's going to be from 100 to 200. So we're going to repeat this. We're going to create a new, so I'm just going to use this here. And I'm going to say this is, remember, price. And this is going to be square feet, which would also be XS and YS. All right, so in this one, we are going to iterate from 100 to 200. So we look at, we do the same thing again here. We have XS, and now this is going to be XS test, which is this. So we create a NumPy array of housing prices where the price is I now, which will be the index value from 100 to 200. So this will be 100, right? Then 101, 102, 103, and so on, all the way to 200. So once we finish this, right? Now notice here that we don't need to create a YS test, right? We don't need to create that because we're actually just, we just want to use the inference function that we created in the training section to see how it comes out in the test section. Now, initially, you may remember that I said that this model is basically y equal 5 times I, and that's it, right? So that's really our model. So plus 0, you could argue. Right? So we kind of set that, right? Because we set that x is I and then y is 5 times I. So we already know that every time you have an I, the price is basically 5 times, or every time you have square footage, the price is basically 5 times the square footage. So we already know the value of W to be 5. All right, so given that, we already know what this inference function should have created given the training data. It should have created an equation that looks like that. So that's what we want to test now, right? So we want to test this by creating a data set from 100 to 200 and then plugging it into the inference function. If we are successful, our output for YS should now be basically 5 times the input. So this should be 500, all the way to, so that's what we should expect there. So now we can test it simply by creating the feed dictionary again. You can call it a different thing like feed test. We're going to provide X test to X. So whereas before, this is why placeholders are useful, because we're going to reuse X. So again, that XS test data that we have is going to be assigned to this X again, our data or this one over here, right? So we go back to the graph. So by doing that, we've assigned the data to the graph again, and we are ready to run the graph again. So we go ahead, we do session run, we give feed test to feed dictionary, that's all good, and then we run eval op. All right, so remember what I said, eval op is just a convenient way of calling the inference function again, but with a different name so that we don't get confused as to what we're doing now. So this is more of an evaluation, not part of the training. So we go back, and if we look here in the code, this, actually remove this comment here. This should be, or we can use either or. So eval op is here, or eval op is here. Both of them should work. But when we run eval op, let's look at the simpler one. Eval op just basically calls y. What is y? Y is the again, our famous, very powerful function. If we want to look at it in the graph, the graph, we know that y is the inference function. So now we just created a new node called eval op. Here we go. Eval op is the node, and that node is connected to y. So when we run eval op, now we are calling that part of the graph that relates to the y, or the inference. So finally, eval op calls, so when we run eval op here, when we run this eval op here, it calls y. So what's going to happen is we go back to this function over here, we call y, we do matmul of the weights that we already have, because we have weights already here, right? We have weights we've learned some weights in the graph. Now the x data is actually xs, all right? So it is the xs test, the new data, and the bias would be whatever we learn. In our case, probably 0, but let's ignore that. All right, and so now what's going to happen is when we run this function, given an x, the new xs test, and the w's that we had learned in the training section, we are going to get new predicted values here for y. All right, so we're going to get new predicted values for y. Okay? And so those new predicted values that are returned, so this function returns a value out back to our code, and those values will be assigned to result. And so finally, once result has values, we can just go ahead and print them. And that's it. That is linear regression in TensorFlow. So when we do this in the lab, we are going to run from 100 to 200, and we can expect our answers to be between 500 and 1,000. So to summarize, from our previous code, x and y, so that the x, so this x and the y underscore, the variables x and y are defined with TensorFlow placeholders. These are used to store our data, whether training or testing. Okay, so this is the data that comes in, the annotated data and the actual samples. So the data you read from your CSV, or in our case, the data that we generated automatically, so goes here, right? That's a critical aspect, right? That's how you should remember that you're using placeholders in a way, right? So the data that came from your CSV goes here. And the syntax to declare a variable to hold the data is as follows. So as you can see, tf placeholder x of float type, and then remember these were the dimensions, so none because you don't know the number of samples, and in our case 1 because we only had the one feature, square footage. All right, so that is placeholders. Okay, in TensorFlow. So notice, that you declare the data type, tf float 32, and you define the dimensions of the x variable. So none and 1 are the dimensions of the featured data for our toy linear regression model. The number 1 means that this data has only one feature, 1, or column. The none parameter indicates the number of rows can vary, basically, and that's really the definition of it. So for this example, x is the featured data, and y underscore holds the labels for each sample in x. Okay, so you can think of it as x and y underscore like that. So that's each of our samples looks like that. The other two variables that, if you remember, W and B, the bias, we go back to our code, right? So that's the variables that we were talking about here. So this W and that B here. Okay, so those values there are also things that we define, right? So they are variables in our code. So the other two variables, W and B, are variables that define the prediction equation. They are the parameters to be learned in the model. So W and B are matrices, tensors. Remember that's why TensorFlow is called TensorFlow, because it's these elements are always matrices. So W and B are matrices whose dimensions need to be defined. And that's part of the architecture of doing this. This is where we start to define the architecture of our models. In this case, the dimensions are 1 and 1 for W, because remember that our model is given a square footage, that's one node, we predict the housing price. Right? So we just have W, but the W matrix actually captures a little bit of the architecture in the sense that we look at the number of nodes here, which is 1, and the number of nodes here, which is 1. This helps us because it allows us to know how many connections we need to have. By knowing how many elements are here, how many elements are here, we know how many connections we will need to have between the two layers. Remember that this is layer I, and then this would be layer I plus 1. So in this case, the dimensions are 1 and 1, and just for the bias is just going to be 1. Notice that we initialize these matrices with TensorFlow a TensorFlow construct called TF zeros. This allowed us in the code to define our matrices, basically. All right. Now, even though we use zeros, as it turns out, it's better to use other values. Usually, instead of creating these with all zeros, imagine we have 4. Instead of creating all zeros, it turns out that sometimes it's better to initialize these with certain specific distributions. So you might do like random, 0.5, 0.2, 0.1, 0.3, etc. And I'll explain in another video why this is useful, but it basically has to do with the fact that we have to do a search in a function, in a space, right? So we have to do a search in a space. And so by doing this randomly, it's like we're picking different locations where to start doing the search, right? Whereas if we start at 0, it might be, we always start at a specific location, and it may just take longer to find the answer. And so that's kind of the intuition with that. In the case of W, the dimension is 1, 1, because it is for a model with one feature x1 and one output value, the predicted housing price, as I stated here. So think of W as a matrix that connects one layer to the next. In this case, we are connecting the inputs to the outputs here, given that there's no hidden layers. In the previous code, we also saw this statement, right? So, and I sort of went over it kind of quickly. When we looked at eval op, right, this section here, and we saw TF reduce, mean, float val, etc. So you might want to know, so what does that mean exactly? All right, so if you look at it, we took a variable float val, and then we ran it through that function. So what does it mean? Well, this statement is used because there's only one value in the tensor. Remember that everything is a tensor. So for example, let's say that we had 996.23, like that, right? So we have that. The function TF reduce, which is this function over here, right? TF reduce, returns just the value 996.23, right? So it goes from there to here. The tensor is, this is the tensor, but we may just want the value 996. So it basically removes the square brackets. So TF reduce mean is a built-in TensorFlow function that takes as input a tensor and computes the mean of it. So it computes the mean of the elements across the dimensions of a given tensor. So it returns a reduced tensor. In this case, the mean of just one value is itself. And so it's a convenient way, actually, of getting our data out of the tensor. And you'll see these kinds of little tricks sometimes in TensorFlow. Whenever you're writing your code, you'll see these approaches. So here we have another example of TF reduced mean. So in the back of the book, I added an appendix that provides a list basically of an appendix with a list of some of these, right? So it has like TF reduce mean, and then it has like an example of how it works. So I think that's a very useful thing to have, because you always come across this code, something like TF reduce mean, within something more complicated. And because of these functions, you may sometimes get a little bit confused as to what is happening. So it's always helpful to go to the back of the book and just check the appendix just to see, these little examples to remind you of what's happening. So in our case here, let's look at an example for TF reduce mean. So given a TF constant, TF.constant, this tensor, right? So that's going to be 1, 1, 2, 2. So we have that tensor, and we're going to call it x. All right, so now we can get the following if we applied reduce mean to just the whole x, right? So the definition is that it's going to calculate the mean across all values. So in this case, the mean of all of these would be 1.5. Now, if you want to do it across dimensions, you can also do TF reduce mean and then select basically the 0 dimension, right? So you're going to calculate it like that. So it's going to be the mean of this and the mean of this, which should be 1.5, 1.5. Now, if we want to calculate the reduced mean across the 1 dimension, so this dimension like that, then we can see that, it's basically this and this. So that's going to give us 1 and 2, right? So we have that answer there. So very handy function, and it's nice to play around with it. I do suggest that you try this in your own Python code. With TensorFlow, run through these examples just to, familiarize yourself with the functions. Remember that just with everything in TensorFlow, you create first a computational graph, and then you have to run it. So to see these actual results, remember you still have to define all over here and then run the session before you can actually print your results. And so if you remember, this section, if I take you back to the original code, is the section here, right? So I know it's, I have a new slide now because there's a lot of information here, but this section here, right, this section here is really what is the most critical part of any TensorFlow code because it defines the architecture. So let's take a snapshot of this that's a little bit cleaner, and you can see it here, right? So this is, I usually like to call this like the core functions. I think I've seen that in some books. Some practitioners call that core functions. All right, and this is basically where you build everything, right? So this is the model, remember as I said, or the inference function. And then remember, this is the part of the optimization, so the learning part, and this is the cost function, right? And this is just the evaluation, if you will. All right, so this is a pretty important section in our code. So let's just make a few comments about it. So again, this is the core functions. So after we define the variables, the next step was basically to define the equation and define the cost function to learn the parameters, e.g. the weights. So remember that's, remember we drew the graph, right? We have the graph, and we saw in that graph that everything was populated except for W and the bias. Those are the two parameters that we needed to learn. And that's, this is where we learn them when we give them the training data. So to do that, we use the following section of code, as you can see in the next slide. This is one of the most important parts of deep learning programming. I also want to emphasize that the code in the segment below is the section that will vary the most for the different models, right? So if, once we start doing a logistic regression model, it's going to change. There's going to be a new cost function. Once we do a neural network, it's going to change. There's going to be a new cost function. Deep neural networks will have new cost functions and architectures, and so on, right? So this is the part that varies the most. So this is where we define the specifics, in our case, of the linear regression model, or the logistic regression model, or the neural network, or the deep neural network. But as you can see, there's now, you start to see a pattern, right? There's a little bit of consistency in the sense that we now know the section that's going to change. At least we know that. And so that's a good thing. And you'll notice that it changes, but it doesn't change as much. So in essence, this is the heart of TensorFlow, or the core of it, or if you're thinking in terms of AI, maybe this is where the brains would be, right? Because this is where all the neurons are connected, and this is where all the magic will happen. Right? So this is certainly very important, all right? And again, it's usually divided into these 4 key sections. So let's look at them in a little bit more detail. So from the previous slide, I'm going to break it down further into just a few more slides to give a little bit more cleaner comments. So defining the specifics of the code means defining the regression equation and the cost function. Here we use the following statements to accomplish this, right? So you saw that we have this one and this one. And these 2 lines of code really do all the heavy lifting. All right, as I said, the brute force of TensorFlow is this function, TF matmul, which ties in really well with GPUs because this is where you perform your matrix multiplications, which allow you to do, which made the difference, right? Which took the theory of of all the people that worked really hard to develop all the theoretical framework of deep learning and took it from just theory to the actual reality of applying it. So this is where that is happening. So the 2 functions then, as I said, are this one and this one, the inference and the cost function. So remember, the inference is just, we call TensorFlow, we call the matmul operation, and we multiply x times w times b. Remember, x is your data, and b, w, and the bias are the model parameters that you want to learn. All right. Then we have this function. Remember, this is tf.reduceSum. Again, one of those TensorFlow functions that are sometimes a little bit tricky that allow us to summarize tensors. I'll describe this in more detail later. Then we call the power, and then we take y minus y squared. So remember that this is just the squared error function, let's just call it. So it looks something like this, right? So this is, what is it? Y minus y hat, right? So the actual y minus y hat squared, right? So that's the model plus the annotated data, right? And then we take the difference of it. So this function is really our cost function. So the first statement, tf matmul xw plus b defines the regression equation. You will notice, actually, as we start doing more examples, that this function is involved in everything, right? We're going to see it over and over and over again. Whether these are real valued numbers, 0.35, 0.39, or they're classes, whether they're like -1 and 1, or they're 0, 1, 2 classes, these values might change, but the structure of the function does not change, right? So there will be the y, there will always be involved a matmul operation here, and then we'll always have x, we'll always have the weights that we're learning, and so on. So that's you know, this function is very interesting because, you know, you will continue to see it as we develop even more complex deep neural networks, etc. So we use TF matmul xw to perform the matrix multiplication, and then we add b to the result. The dimensions of the b vector need to match the dimension of the j index of the weights vector. So remember that whenever you define the weights, you know, as we did before, 1, 1, right? This was the dimensions of the weights. The bias just needs to be whatever this one is, whatever that means. So that's one. So that's kind of like the rule of thumb, at least for now, for us to worry about. And that simplifies quite a bit. Later on, I will also show you some tricks that we can follow in terms of how to write the code, so it's very easy to figure out these values just by drawing our graph, our network, and then plugging the values in here. As a side note, I will point out here that TensorFlow is designed to be used with GPUs. And GPUs are very good at matrix multiplications. And so the function matmul is the one that performs these operations. So that's why I keep saying that this is where all the heavy lifting is performed. Right? And I think that's an important thing that you should understand, how the code here ties directly to the hardware and to your GPU, although this can also run on the CPU. Is just a bit slower if you have a really large data set. So this is, in essence, the power of TensorFlow, in my opinion. The other line, the cost function, so this is the cost function, right, is made up of, you know, it basically consists of a reduced sum, the pow, and everything. This defines the cost function, as we talked about it already. So y minus y hat squared, right? So the sum of these, the sum of the squared errors, the famous equation. I usually like to start the discussion of TensorFlow with this because we've all heard of this, or a lot of us have heard of this before if we've taken a stats class and we have some familiarity, plus it is intuitive. So this, as you know, this is the standard least square cost function in linear regression. Now notice here a few functions, TF pow, which traces the difference between vector y underscore and vector y to the power of 2. Right, to capture that essence. This result is passed through the TF reduced sum function and assigned to cost over here. Now, the function TF reduced sum, notice that this is different, right? This is not the previous one that we looked at. TF reduced mean. This one is TF reduced sum. All right, another one of those handy TensorFlow functions. This one also, I've created, as I said, an appendix in the back of the book that provides a list of all these functions with a few examples, and it's a handy tool to have whenever you're reading code and you don't quite remember what it does. So here we can define that TF reduced sum computes the sum of the elements across dimensions of a tensor. So in this slide, we are going to discuss another one of those useful TensorFlow functions called TF reduced sum. So TF reduced sum is, as we defined previously, computes the sum of elements across dimensions of a tensor. All right, so let's see how that works. So imagine we have x, right? So we have our x here is a constant, which will be a matrix 1, 1, 1, 1, 1, 1. And so that's our matrix. So if we want to use TF reduced sum, if we just do sum on all x, the answer is 6, right? So we just take the sum of all values. If we want to take reduced sum of x across dimension 0, we're going to do it this way, right? And so we end up summing these values. So we end up with 2, 2, 2, right? Additionally, if we want to do reduce sum x across dimension 1, right, we're going to do that. And so that means, it turns out, we're going to do this one and this one. So that should be 3 and 3. Right? Because 1 plus 1 plus 1 is 3, and 1 plus 1 plus 1 is 3. So that is basically the way TF.reduced sum works. It is a very handy TensorFlow function that you'll come across. And it's just one of those peculiar things that are specific to TensorFlow because it uses tensors. So now, if we look back to the code, we've covered these two elements, 1 and 2, and now we're going to focus on number 3, which is the gradient descent optimizer. Let's call it gradient descent. So whenever we want to reference the cost function, right, which remember this was defined in the graph already, or the regression equation, we can just do so by the variable names we define for them, which are y and cost. So you remember this is what we talked about when we discussed the graph, right? So we had that very handy little graph, and we know from this, from this graph here, again, I'll point to it, that this graph is really where everything is defined, right? And everything is interconnected through the graph. So whenever we want to grab an element, we just have to call the name of one of the nodes, the node that is pointing to it. All right, so in this case, so whenever we want to reference the cost function or the regression equation, we can just do so by the variable names, that is the names of the nodes that we define for them, which in this case are y and cost in this case. Once the cost function is defined, we need to, the next step is to tell the model what optimization to use, right? And that's, in this case, this line, gradient descent. Remember that we have this parameter, and this is the part of the graph that we are going to call. And whenever we want to run the whole thing, we just call train step, right? So by calling train step, we basically run everything else. So this indicates that we should use gradient descent optimizer with a step of 0.01. If you remember, this step was that example of the giant walking over the mountains, or the mountain range. So this object, train step, is now the optimizer itself. It's now the optimizer which references the cost function via the variable cost. Okay, and you see that here. So again, we call this one, execute all of this, and reference the cost function. And as you remember, cost itself is linked to the regression equation via the y. So here we have, I've copied the graph actually and moved it a little bit. So this is, if you remember, when we were defining the code, when we were defining all of this code here, right, we said that this code actually resulted in the computational graph. So I've moved it here again just so that I can reference it a little bit more conveniently. But if you remember, this is everything, right, including the placeholders, variables, that we have to learn, and everything else that we are calling. So if we go back to train step, right? So if we go back to train step here, we know that this object train step is now the optimizer. So that's in the code here, right? So train step is this, and it's going to call the cost function variable. So cost is here. This is our cost right there. And just remember that this cost then defines, you can see here reduce power, and you reduce or you minimize the sum of the errors of the real value data versus the predicted data. So this object train step is now the optimizer which references the cost function via the variable cost. So you can see that, you can see that here, right? Cost. And cost itself is linked to the regression equation via the y, right? So cost is related to y, and you can see that here. So cost is here, again through here, is linked to the real y, and also, but more importantly, to the predicted y over there. Okay. The final part of this code segment just takes the predicted y value and performs typecasting and reducing operations. All right, so if you have a vector of values, the average all of them and return one average value. Okay. So once the inner workings of the model are defined, okay, the next step is to move to the session definition and the main loop. So that's, kind of the conclusion. So I'll just say a few things about this. In the code segment below, we can see that this process involves defining init and session. So you can see here, this is basically, where we define the session. All right, and you can see that there. So once we've defined the architecture, once we've finalized our graph, remember that once we create the graph, this is like object-oriented programming. We've defined a class, but we don't have an instance of it. So in a way, defining the session is like creating the instances of it. Okay? So for that, we have an init variable that conveniently calls something in TensorFlow called initializable variables. This is the thing that basically creates now space and memory of type float, of dimensions n and 1 and so on. So this initializes all variables and placeholders, the tensors, in the graph once you run session. Consider that at this point, all we have done is define the graph, although it's a beautiful graph, right? So it took a lot of work just to get this, right? But consider this is all we've done. We haven't actually trained anything. We haven't tested anything. We haven't even run our data, but we have this amazing looking graph. All right, so at this point, we've defined the graph structure without actually running anything in TensorFlow. To run things in TensorFlow, remember we have to use session.run with the variable we want to run in it. Okay, so that's the variable we want to run. In this case, we want to initialize the variable, so we run in it. All right, and you can see that there. Finally, the last part in our linear regression code was to run the main loop. All right, that main loop. So let's say the main loop. Okay. To actually train and test the model. In this case, we've broken up the main loop into two separate loops for better visualization. The first loop is for training, and the second loop is for testing. And the first training loop is very simple. The training data in this case was not read from a file, but instead it was created automatically, just to make this even easier. I wanted to get rid of the whole having to read a file complication, dealing with all the dimensions, etc. And so we could and also it shows us that we can just create our own data really quickly to better understand the algorithm. The feature vector was stored in XS and contains only one feature, X1, remember, which was square feet for the housing prices. The feature represents the size of the house. And the corresponding housing price for each XS is stored in YS. So remember, for the scenario, each housing price value was 5 times its corresponding house size. Therefore, our model after training was equivalent to this one, right? So we have Y 5 times, and let's do this instead, X1 plus B, right? So that was our model where B was actually 0. So it turned out just like that. In this case, the training phase would optimize the weight vector to be equal to 5. So remember, we didn't actually give a W and assigned it to 5. Instead, we gave it training data. We gave it the training data which had the X data and the Y data, and the model learned this. Right? So we saw that it actually did learn this because it gave us the expected value. In the for loop, the process is repeated 100 times, which is basically saying that we trained it, we gave it 100 samples, and it was able to see the pattern. once XS and YS are defined, these values were assigned to the feed dictionary. And you can see that in our code here, right? So we've done this part and this part, right? And then we created the feed dictionary as described, which assigned the YS data to Y underscore and the XS data to X, right? Which are the placeholders. All right. Now, what is this feed dictionary? I kind of wanted to describe it a little bit better here in writing. So this is an internal mechanism of TensorFlow that is very useful. So this is an internal mechanism for TensorFlow that is very useful for passing the data from the Python code, XS, right, to the TensorFlow graph. So remember that if we go back to our wonderful graph here, you know, the XS and the YS that we created, you know, need to be assigned there and need to be assigned there. All right, so that's how the feed dictionary actually does that for us. So in this case, XS is assigned to X placeholder and YS is assigned to the Y underscore placeholder. These variables are the same ones that we already defined in our code. The last part is to run the graph. Finally, this is where your TensorFlow code will run. Before now, the code had not executed, but after session run train step, the code finally executes. Okay? In this case, we run train step, and everything that is linked to train step will run. Right? So remember, train step was here. Right? If you remember, this is train step, right? Over here. And train step basically calls gradient descent optimizer and calls cost. Okay? Calls cost. So really in the graph here, train step, let's just put it over here, train step is a new node that we created linked to gradient descent, with a parameter of 0.001 step, and then it calls our cost, and that's how we are able to access everything in our graph. In this case, we run train step, and everything at that point, all the data is linked, the model is linked, we've told it everything that needs to happen, and TensorFlow will do its job. So we run the gradient descent optimizer at this point, the cost function for least squares estimation, and the linear equation. So everything gets run all together. You know, again, we can go back to the graph and you can see that, right? So we have the train step, calls gradient descent calls cost, the node is reduced power. If you remember, this is this part square. Here is this one is that one, and then this one is this one, which links with a matmul x with w, and we learn the parameters that way. Okay? So that is how this works. And finally, we are done. So here we can see, so we run the gradient descent optimizer, the cost function for least squares estimation, and the linear regression equation. And here's the code summarized. So after we gave it the feed dictionary, we do session run train step with the feed dictionary, we run the graph, and now the model is trained. So this is the train loop. Right? This is the train loop. The second loop, if you remember, which was this one, this was the test loop in the code. This was the test loop, very similar to the train loop. You don't actually need two loops. I just did it to make it even more obvious for academic reasons, but you don't really need it there. So the second loop below is very similar to the first one, except that it is focused on the testing phase. So now the model is built, right? So that part of the graph, imagine, now has W's and B's, right? So all you need to do is replace then the X's again and you can use that part of the graph, the equation, to predict the y. So here we use the model from the training phase to predict the housing prices given the house sizes for the range of values from 100 to 200. So if you remember, in this case, we do a range from 100 to 200. I is basically this I, so we generate a new XS test, right? And then this new XS test is assigned to X in the feed dictionary. And then we just run eval op. All right, so that is equivalent to going to the graph and now knowing that this y here is the equation. These values are already populated, right? And then we just replace this x, right? We replace that x with the new XS test. So XS test gets assigned to x. And now once we've done that, we can go ahead and run it because we linked eval op to y. So that means that whenever we run that node, we can actually run the y and predict the values again. That's what happened. So we are able to predict the values. The data was created automatically here for this example, and notice that here we just, in the session run, we just call eval op, which is what I just described. So that's eval op. Finally, eval op calls y. Y returns a value that's assigned to result, and then the value of result is printed out here. Right? And then we have our result. We have our values, our housing prices given square footage. The variable eval op is linked to y, which is basically the linear regression model. So here we use the trained model, but with a new data set, XS test. The result is stored in the variable result and simply printed out. The result of the classification should be that the regression model predicts housing prices that are 5 times the input house size. And the outcome can be seen in the next slide, which is there. So we gave it a range from 100 to 200, right? So these are the square footage, and then it predicted, so this was XS, and this is YS, right? So it predicted housing prices, which are 5 times the original input. You see that there. So this is the result from running the classifier. So when we do the lab in the next video, you will be able to implement this code in TensorFlow, run it, and be able to obtain these similar results. So this will be your first actual TensorFlow code, and basically it should cover a lot of the elements that are going to be consistent as we start building deep neural networks. So the previous code for linear regression. So the next sequence of slides is what I would call modular approach, right? So some practitioners, we all know what modules are. We all know about writing code in functions instead of sequential code, right? So, and that's basically what I'm gonna do here is just kind of rewrite the previous code now that we understand it in a more modular format using functions. And the advantage of doing that is that we can basically, just like I grouped the code by numbers, and I said, most of the code will be one, we'll have these core functions like here, right? So I said we'll have these core functions 1, 2, 3, and 4. Well, but we still kind of have like mixed up code here, or we have 4 lines of code like here, and then other times we might have 2 or 3, right? So it might be nice if we divide these 4 sections and other parts of the code into functions, right? So that way we just have 4 modules, and that just makes the code a little bit nicer, easier to read. So that's what this section is about. So it's really just about rewriting what we just learned, but this time with in a modular approach. All right, so let's go ahead and do that. So modular approach. So the previous code for linear regression can be rewritten in a more modular form using function calls. This approach will be very helpful later on, as most implementations can be written in this same way. So that is to say, as we start to do logistic regression and we start to do neural networks and deep neural networks, etc., we will always have, or most of the time have an inference function, the cost function, the optimization function, and the evaluation. But in the inference function, for instance, whereas before we just had that linear regression equation, in other algorithms like deep neural networks, we'll have more complicated architectures. So we'll need to have more lines of code to represent more layers, more functions that go from one function to another to another. All right, and that's the same for the cost function, right? So the cost function is not always going to be least squared errors. It might be other cost functions. And so it's nice if we have these 4 functions that we always need, and then all we have to worry about is the code that goes inside the functions themselves. All right, so that's what we're going to do. So this approach will be very helpful later on, as most implementations can be written in the same way, and the only thing that changes is the internal definition of the functions themselves. Okay? So this new modular approach is what we're going to look at next. So at first, I'm going to show you the original code. So just to remind you of what it looks like. So here it is. So remember, we have the libraries, placeholders, variables, the core functions, 1, 2, 3, and 4, right? So these are the main things that we're going to now write as functions. And you'll see how we can group them. It might be convenient, for instance, to group, if W and B are only used here, maybe we can just take these 2, combine them with the equation, and have them, the 3 of them, be part of just one single function, for instance. Right? So it just, we're going to rearrange the code a little bit more. Other parts of the code, like this one, doesn't have to be written in a modular way, because it's really just things that we run once. And then what's going to happen here is that, very little will change here. These train step, if you think about it, and eval op are the only node. These are the nodes that we're calling specific lines of code. So now what might happen is they're calling functions instead, but very little has changed. So that's the original code, and now we're going to take and convert it into a modular approach. So you can see here, this is the linear regression code. Linear regression code. But now rewritten in a modular approach. So modular approach. All right, so let's take it one step at a time. So we can see here we still have our libraries. That hasn't changed, right? TF and NumPy. Notice now, however, that this is, we define a function called inference. The input to it is x, right? And really, if you look, it's really just W, B, and Y, right? So W, if you remember, is just the variable, right? Same dimensions, that hasn't changed here, as we explained it before. The same goes for the bias, and these parameters are used here. And then all that happens now is the inference equation Y needs to be returned. And we need to provide to it this input x, right? So that's really all that has changed, but everything else is still the same. So we just rearranged the code that we had previously, right? So this code, we rearranged it, so these 3 elements basically, into a new specific function. Then we have, for the second one, we just had the TF reduced, TF power, that's, the least squared error. This one line of code, we really, that's all we need, but we can define a function called define loss. Remember that this takes the real values plus the predicted values, and so those values are basically passed into the function over here, but otherwise nothing else has changed. And now we just have a nicer way of grouping this. Now it just so happens that sometimes these cost functions can be a little bit more complex, so we can add lines of code without really affecting the readability of the code, right? It helps us to have code that's kind of standalone. The next one is to take the gradient descent. You can see that here. We just take gradient descent with the cost function. Notice that now we pass cost, right? The cost is this one in loss. Remember, we return it. So the loss function will return cost. So you can imagine that cost is in a specific line, and then it'll just be returned there and passed to the training function. So we can call this function training. That's number 3, right? And we call, as I said, train step calls gradient descent, this value. We pass the cost that goes from here to there, and then we return train step back to the algorithm. And finally, the last part, remember we had those 4 lines of code that looked really messy. You know, we had this does not look very nice in the code. So by having a function, now we can just take all of them, put them in the function, and just, it makes for cleaner code, really. All right, so now we have evaluate. Evaluate can take, you know, some values. Usually we're going to take the predicted value from here, the inference, this value, right, and then the real values from the placeholder, right? We're going to take those and compare them. But in our case, actually, remember, all we did is we called the inference y, and then we would run it with another variable, basically. And that's it. That is modular programming. So this is a nice way of rearranging the code and grouping it within 4 specific functions. Here again, you can see the evaluate function. It's kind of, you know, it was cut off from the previous slide, so you can see it again. And I've already explained all of this, right? So we talked about the cast and the reduced float, just to kind of format the data better. Okay. Now, because we've done this and defined the functions, it means that this section, this section that we have here, this section here, will now need to be rewritten, because all we did so far is that the definitions of the functions were like added, you know, like somewhere in here we added the functions, right? But we need to call them. So now this section, instead of having code, it'll just have function calls to that code. So the core function or the core section is still there, but now it's just made up of function calls. And we can see that here quite conveniently. So we might want to add like a line here. And if you remember, this is just x and y as we had it before. Nothing has changed. Those are the placeholders, right? And then now this is where we have the function calls, right? So we're just calling our individual functions. So if you notice, we give it x, we call inference, right? So inference just means that we call this one, right, and execute that code. Inference returns y over there. You can see that. So we get back our y here. Then this y passes to the loss function, right? The placeholder, y underscore passes there, and these are assigned to loss, so we call the loss function. We go back. This is the loss function. So the loss function then performs the reduction, the least squared error. All right, so we provide y here and the other y, so these parameters, right, flow there. All right, and this returns cost. All right, so we go back to our code. So now loss returns the cost, so we have that value here. Then cost will be passed to training, right? So that means we call training, go back to the training definition, and we have training here. Here's the cost, and it flows here into the minimize of the gradient descent optimizer. We run this, we return train step, and train step then is here, and that's it. At this point, we have train step once again, so this can be called from the main loop. So if we go scroll all the way down, you can see that train step is right here, right? And this code here has not really changed at all. It's still the same things we had before. So, and the same applies to eval up, so I'm sure you get it now. You know, eval op just we actually, even though we provide the real data, we're not using it. We're just providing the y from inference here. Right? So this y is what we're providing. We go to evaluate, and evaluate simply takes the y. Right? So if you look here, takes the y, it passes it through casting and some other changes, right? And finally, it goes, from here to prediction float, and we return that value. Ultimately, you could argue that you just returned the same thing that you had at the beginning, because all we're doing here is changing the format of it. All right, and finally, that is assigned to eval up. So whenever we want to run eval up, which is basically calling the inference function from the graph with new data, the test data, we call this eval up here. As you can see, this has not changed, so this is still the same. And then in the main loop, nothing has changed here, still the same, creating XS, YS, the feed dictionary, but running train step. That didn't change at all, except that now it does function calls. Then for the test part, remember this is train, and this is test, right? It's the same thing. We create XS test. We are actually not even using that, so you could scratch that out if you want. This is just a different way of writing the code, so we're not using that. This is the feed dictionary. We don't really need that, or the comma really. And then we just end up running eval up. Remember, eval up just calls y from the graph, which is so that's equivalent to saying I learned this w, I learned this b. Oh, and by the way, this is going to be XS test, which is my new test data over there, or this one here, right? That one. Okay, and so once we run eval up here, basically this equation is evaluated again with the new test set. So that's equivalent to saying, given these new square footage data from 100 to 200, right, this data here, now I'm going to plug it into the equation, and this will predict a new set of y's, which will be a new set of house prices, right? So from 500 to 1,000. And that is the result that we got when we looked at this. And as I said, when we do this in the lab, we run this code in the lab, you'll be able to see how it all works together. So it's pretty straightforward, actually. And this is a very good example, because what I like about this is that we learned linear regression. We actually learned a lot about TensorFlow in this example, and we learned that by doing modular programming, we can structure the code in such a way that we know what needs to be changed, depending on the model that we're using. We know that if we're using neural networks, deep neural networks, or linear regression, the main change, the main architecture needs to happen here, right, in this equation, which basically translates with our new modular approach that this is where the architecture will be defined. It turns out that for the most part, we will always use gradient descent, and this will change as well, because this is LSE, right, least squared errors. It's specific to linear regression, but logistic regression and other algorithms will use different ones. So mainly, whenever we're using our modular approach, the main changes will happen here and here, right? And that's a very critical thing to know. And also, by doing code like this, it just makes it a lot easier to read, to write, and to understand. And so finally, once we obtain a result over here, then we can just print out the results, and you can see that there. All right? So as can be seen from the previous code examples, not much had to change in the code to make it more readable, modular, and easier to modify in the future. And that's really the key. That, as I said, this same approach will be used for logistic regression, and then for neural networks, and then for deep neural networks. The new aspects are that we now had 4 functions that can be used to define the model. They are inference for the equation, loss for the cost function, training for the optimization, and evaluate for the performance evaluation. As we move forward, we will try to use these same names and these same functions and just modify the internal definitions of the functions. So in summary, we discussed linear regression in TensorFlow. We learned basically one of the most important issues is that we learned specific mechanics of TensorFlow, right? So we learned how to code and some of the main elements of the TensorFlow programming language. We also learned about linear regression. We went over some of the theory of linear regression, right? And we learned how to model linear regression in TensorFlow. So how to model it in TensorFlow. We also learned about graphs, right? So we learned how the computational graph can be created from the code. So we learned how to go from code to create this computational graph. And finally, we learned about a modular approach that we can follow. So we learned about a modular approach that we can follow to make creating, linear regression, logistic regression, neural networks, and deep neural networks, right? So we learned an approach that we can follow that can be used for all of these, and hopefully it'll make everything easier to understand, to read, and to write. All right, and that concludes our introduction to linear regression with TensorFlow. In the next set of slides, we will do, the next one will cover logistic regression now and how to implement it in TensorFlow, and we will also do a lab to run this code for linear regression.